तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome. Now that you have had a good review of digital circuit design, and it is ripe time for us to pick up HDL coding of the same. And digital system design is primarily a combination circuit and a sequential circuit combined together in any mix, and as you will be seeing as we progress further. And to start with, we will be learning about simple combination circuits using Verilog, and we will also be covering a little more more complex circuits in combination circuits, and thereafter we will be going on to sequential circuits, and ultimately proceed to digital VLSI system design as such, using of course Verilog. And before we go into the combination circuits, we will just see the evolution of HDLs as such. Primarily HDLs were used in order to speed up design cycle time as such, and hitherto schematic circuit diagrams were used, and it was very handy for designers who had been accustomed to designing systems using discrete digital ICs, which you know 74 series and so on. And the problem with the schematics when it comes to VLSI design is that we will have to struggle with hundreds of drawing sheets of the size A1, and it has other disadvantages such as entry time is very high, and you have to use Karnoff-McCluskey, Quinn-McCluskey methods of optimization, and you had to wade through hundreds of drawing sheets, and readability is poor, and these disadvantages outweighed the need for HDLs, and the HDL has brought about, so to say, a revolution in digital design, in the sense that the cycle time reduces very dramatically, and from my experience I can say there is 3 to 5 times speeding up of cycle time I could see, and it provides a very concise presentation in contrast to the schematic logic diagrams. This is in sense there are what are called behavioral statements and RTL statements, and all this can lead to very concise description of the digital hardware that you are designing. And in contrast to this, in schematic you have to really put gate by gate, and it will take quite many quite an effort to achieve the same end result. And there is no need for K-map and Queen-Mickens-Key way of reduction, because synthesis tool is supposed to take up this role. And HDL designs are portable from one vendor platform to another. For example, you have developed your HDL, let us say for Altera platform, you can always migrate to another vendor such as Xilinx. And it is also technology independent, in the sense a few years back it was 0.65 micron technology, thereafter 0.5, then 0.35, then 0.135, and now they are embarking on 0.09 micron technology. And all these technological changes had no effect on HDL. That is to clarify, I mean whatever you have designed earlier when the technology was low, and the same design will precisely work in the present technology, and most assuredly on new technologies as well. And two most popular HDLs used currently are Verilog and VHDL. One may this is for the in the realms of digital circuit design, and there are recently Cadence has come with mixed Verilog analog and digital circuits design, and they call it Verilog AMS. And you can implement A to D converter, D to A converter, and PLLs and the rest of analog circuits, and you can mix it with the digital circuit as such. And it is needless to say, emphasize that Verilog and HDL can be used in circuit design ranging from SSIs to VLSIs. So you may regard up to 500 transistors to be falling in SSI category, and beyond that and below 5000 for MSIs, and beyond 5000 up to 50,000 this LSIs, and beyond that they are termed as VLSIs. They are a number of transistors what I am speaking of. We will be using Verilog in this course for digital VLSI system design. Verilog is a hardware description language as such. It was developed originally by Gateway Design Automation in '84, and Cadence popularized it later on. And in 1987, synthesis was introduced using Verilog by Synopsys, one of the leading vendors in ASIC platform. And Verilog has become an industry standard, as you know, and because of its simplicity, you can quickly learn Verilog. In fact, it is easier than learning VHDL in my experience, and it has a C-like structure and very fast design cycle times. And the C-like structure, what I am saying is you can use if then else statements, case, then for, while, and the rest of it, and even IO structures are more or less similar, and of course there are differences which we will be learning gradually. This Verilog has been very popular in high-tech areas of USA, the West Coast belt, and whereas VHDL in the eastern coast. And real reason may be that industries preferred Verilog and institutions preferred VHDL, but it is only a general observation, and it is not there are always exceptions. And you as a designer can start with let us say Verilog first, having mastered it, you can switch over to VHDL later on, because it all depends upon what the customer requirement is. So, so in this connection we will take Verilog in this course and specialize on it, and both Verilog and VHDL are conformed to IEEE standards as such. We have already seen that Verilog is a hardware design language which is very much akin to C, but you should bear in mind Verilog is a hardware design tool and not a software design tool, whereas C is clearly a programming language which basically runs sequentially unless you veto it by calls and the rest of it. And whereas in Verilog, although it resembles C program, but you should know that they are all concurrent statements as such. So it is precisely the same as a digital circuit design making use of the conventional TTL gates. Verilog allows different levels of abstraction as such. One is behavioral. What we have already seen is if then else structure and while for, all those things would form behavioral. And there is another structure called data flow structure. This basically concerns with flow of data from one place, one register to another and so on. And we will see quite many examples as we progress. And for those who are used to gate level simulation as in schematic entry earlier, and they can still use gate level primitives, and if you want to get extra timing closures, probably you may have to use gate level primitives as well. And next most important thing is register transfer level, and it is called RTL. This is the core of digital design as such, and if you violate RTL, synthesis tool will promptly reject. So this is only to ensure that the final product that you are going to tape out will be really working on the hardware that it is meant for. And there are finally you can use even switches, say NMOS, any MOS switches as such in case you need. And the problem with this switches is it's technology dependent as such. And so best what will be concentrated on this present course will be this RTL type, and occasionally going for data flow and behavioral type. And on very rare occasion we will go on gate level. As an illustration, we may consider gate later on. So we will start with the combination circuit using, say, simple assign statements. It is as simple as what you read there as assign, and some of the examples that we will go is for very primitive gates as such. To start with, we would like to make a buffer. So what all you have to say is, if you see the input here, it is A, and the output naturally after the buffer is once again A. So the output is F1, A is the input. So if you see the corresponding Verilog statement is assign, this is the important thing, mandatory in order to assign any statement. So this is the output on the left hand side of the equal to, and it's almost like a C program, right, with the exception that assign is a new thing here. It's because this is a hardware field where and similarly, if you want an inverter, what all you have to do is instead of A, just invert. This exclamation mark is a inversion signal, and this is basically a logical inversion as such. So you can use it for multi-bit precision also, this very same symbol. And here in this place you can use the symbol tilde, which is bitwise negation. So, and you want to do AND or OR with two inputs. It's once again as simple as that. What you need is one more symbol you had to know. It's an ampersand and this vertical slash here. This is for OR, this is for AND. And likewise, whatever gates you have already derived, and you can get its inversion. For example, NAND, which can be derived from complementing AND. So, what you had A and B earlier, you use the same inversion signal here, and so is the case for NOR. Once again you see here inversion here, and for exclusive OR and exclusive NOR, once again you see the inversion, and for exclusive OR the symbol is hat. Now that we have seen how to use assign statement for simple combinational circuits, we can also implement the same using always statement. This is always is actually a block of instructions which you will be seeing from some of this, and prior to writing a code for this, we will just take a simple circuit such as a majority logic here, and this is nothing but AB plus BC plus CA, all single bit signal as such, and you need two input AND gates and one 3 input OR gate in order to achieve this, right. And next example we can consider is how to concatenate different signals. For example, ABC are each 1 bit signal. You can put it, concatenation is just putting it together in the order that you want, and this is the flower brackets is the one which signals the compiler that this is concatenation as such, and you separate the signals, and one may be tempted to say variables. That is because of our past habits linked to the C language, and here I do not speak in terms of variables, but as signals as such. Any digital node is a signal, and whatever IO you have in your system is a signal as such, and as usual you can assign this final output to any other signal name that you want, and let us say when you do this, it implies this A is in the MSB. So, always left side will be the MSB in all the treatments here, and naturally it follows suit. I mean the last bit is the LSB, and next example we will be considering is right shift and left shift. We will shift by just 1 bit in this case and 2 bits in this case. When you shift, let us say we have a signal which is 3 bits wide. In fact, this F10, if you notice, it was derived from concatenating 3 signals as such. So, when you after right shift, what happens is the first, these are all the weights, you know, that 8421 codes. So, probably I should have put it right on the top. This is not a data as such, it is a bit position that I have referred here. And once you right shift this one, what you are going to do is just shift it here, then this 0 bit position, whatever data is in that position, it will get lost because we are not storing it. And if you want to store that, you can use some other Verilog statement to store in case the need arises, otherwise you do not really bother about that. So, similarly 2 and 1 will occupy 1 and 0 of the target. So, here and once this 2 has been used up, this becomes vacant as such. It is unoccupied bit is forced to a 0, and if it is left shift like this with the 2 shift here, naturally this bit will come over to 2, and these 2 bits will get lost, and in such a case this bits vacated will be occupied by zeros. Now, what we have seen over 2-3 pages, we have contained the entire thing in a single page here, the program as such. In fact, you recollect what we had done earlier is we have realized the majority logic, which is AB plus BC plus CA. So, note that ampersand stands for and vertical slash for OR, and that is how you get AB, BC plus CA. And this is precisely a part of program as such, code, Verilog code as such. And you would notice there is one always statement here, and what all it means is whenever inputs such as A, B, C and F10, any of these inputs changes, only then this will become active, otherwise not, right. This instructions will be so to say executed only when any of these inputs change from the previous value, right. And if you have multiple statements like this, you need to put a begin and end indicating the whole thing is blocked as such. In one block you can put as many instructions as you want really. And another thing is when the statement is complete, you just end up with a semicolon there. If you forget this, compiler will promptly report error as such, and we will be learning all those gradually. And next example was concatenation, as we have already seen, and it is precisely what we have seen pictorially there. And these are the flower brackets which concatenates ABC signal. Suppose you want C as MSB, you should have put, let us say, C here and then A comma B in the in any order. Suppose you want in addition to this you want to add some 3 zeros at the LSB. What all you have to just add is put comma here and then say 3 stroke B 000 or any other data you want. If you put 111, 111 will be concatenated towards the LSB side, right. And so is the case, you can insert anywhere or you can, instead of that you can put any other signals which already is available here. And we have also seen shift registers, write shift by 1 bit here and 2 bits here. It is as simple as just one statement here, right. So what happens here is after write shifting by 1 bit, it does not affect this F10 itself, that is the source. You can make it affect some other signal as such. Say in this case I have named it as F11, and that is the beauty of this statement here. So is the case with left shift, and you may also note that you can put any number of bits all at one stroke, it will do the shifting as such. So suppose you want 10 bits shifting, you just put replace this 2 by 10. Now we will go into little more complex things, say such as multiplexer, which you have already covered in the review. Let us consider 2 input mux as such with I0 and I1 as the 2 inputs, and A is the selected input. If A equal to 0, it automatically selects I0, and otherwise it selects I1 and outputs on the mux2 as such. And in order to write this, what all we need is a single line, and once again using assign statement. Only difference is there is you notice that as far as the output is concerned, it is precisely same up to the equal, and here you have a select signal, and this select signal must be first put here, and within brackets if you can put here, and this is not the only way of writing. In fact, you can dispense with all this here including the brackets and just have A, plain A, then also it will work. And or if you want, designers normally prefer putting 1 stroke B 0 or 1 like that, because that will give an indication that how many bit precision this signal is. Here of course it does not arise, and we can put it need not be necessarily this alone, we can have even multi-bit thing here as an assignment here. And question mark is once again mandatory thing, and for the mux this structure at once reveals that it is a mux implementation, and it has 2 inputs as we have already seen, and the first input that you write is not this I0, please make a note of this. We will have to write I1 first and then followed by a colon which separates first input, I mean this input from this first input. This clear, I hope. And you see here 2/, and this is basically a comment field as such. So once you put this is a line comment, and in like C you can use /* and */ for more than a group of lines as such. For a line you use this, and you can either put it here. For want of space here I have just folded it here and shown here. You can in fact put right along with. So now we will make it a little more complex by going for 4 input mux as such. Let us consider I0, I1, I2, I3 are the 4 inputs that you want, and naturally this calls for 2 selector pins as such. They are C, and note that both have been used I mean same C is used for both, and that is one here B, and this happens to be the MSB. You should be clear which is MSB, LSB, because otherwise you will the whole thing will become chaotic, because the tool I mean only treats in that particular fashion. For example, this is always a higher order input as such, and you see this one inside this is precisely the same 2 input mux that we have used earlier, except that inputs and outputs are different. And once you say this one, whatever is the output will be actually be in this position, and that particular thing will go as the second input as such. See, for example, to make it more clear, let B selects this, this is the MSB we have seen, and if you notice here I0 I1 is coming over here as the output of first mux, and second mux output is derived from I2 and I3 here. So by selecting B, for example, you select, I mean make it 0, then this will be selected. When this is selected, which of this will be selected would depend upon C here. So naturally you can very easily select one out of the 4 signals as such. So is the case with this, and for one it takes this, either it selects I0 I1 or I2 I3 and assigns it to the very final output mux here. And word of caution here is you should avoid such nesting as such, because for simple reason that you notice that there is a gate delay here, and this gets plowed into another mux, and that in turn will add more delay, and if you keep on doing this one, finally you will get a very delayed output, and if you are to use this in between sequential circuits in the data path, naturally your speed of operation will get hit. So this is not a good practice of nesting. So the designers have unwritten law saying that they will not go beyond 2 inputs as such. You use only 2 input mux in this form with the assigned statement in this form. And then what is the remedy for this? Suppose in real life situation it is not merely 2, it may be 20 or 40 or even hundreds. So what do you do for that? And you have to make an efficient hardware design, and the way out is to use case statements, which we will be seeing right now. For example, we have gone to 8 input mux as such, I0 through I7 are the inputs, and once again ABC you need 2 to the power of 3 here for selection, and once again ABC is the MSB, which you will have to keep track all the time, and mux 8 is the final output as such, and we will be using always and case statements together in order to achieve this. And notice that suppose I want 64 inputs, it is all child's play. We have only to just add few more statements which we will be seeing. See, what you have seen there earlier is a mux circuit, and this you are already familiar. It is an always block with always a begin here and end here, and now we have added one more statement called case here, which is very much close to C case, and except that this is actually hardware design, should bear in mind that. And we have also seen a concatenation of 3 numbers here, and that is how we put within brackets. This also is a mandatory thing. That means to say a single signal can be put here, or any other multiple even statement can be put here, right. And so what all this means is, when ABC each of them is 0, that is corresponding to this, what we should get is I0 at the output, right. And similarly if it changes for different values, let us say 111, naturally I7 must be selected and output to the mux 8. So it is as simple as that, and notice that we have only put one statement here. So occasionally you may have to put multiple statements, in which case you start don't fail to put a begin and end towards end of that statement as such. And when we will be going for a demux implementation, which is exact counterpart of this, then we can see more details on that. So this is as I said, it is inverse of mux 8. That is the reason why I am putting mux 8, which is the output in the earlier case, as input here. So you naturally, after this process, you naturally get back what you have plugged in as inputs there. So, this D naught should correspond to I naught and so on, I7 to D7, and once again here you have selector, once again A is the MSB here, and this appears to be little more complicated because this is once again using same always statement, and whatever is the inputs that are being used here, and note that mux 8 is also an input here, and you have to list all of them, and notice that it is only OR, no AND is valid here, right. It only says this signal or that signal and so on, it is only an OR case, there is no such thing as ANDing there, there is no logic, this is not a logic thing, it is plain English statement as such. So, and what it does here is it reads mux 8 as the input, and then depending upon ABC inputs, it assigns to that particular output that you really decide. For example, if it is 0 0 0, we notice that mux 8 must be routed to the D naught output as such. So, that is precisely what is being done here in this statement. So, mux 8 which was the output of the multiplexer earlier, 8 input multiplexer we have seen, and assigns it to this D naught here. And you notice that D1 through D7 are all made zeros here, because when it enters, it can enter from any other state. So, unless you make them zeros here, and it would it may hamper with the performance. It may have come from latch, and it may latch onto the old signals, right, and it is better to give this here. And you may notice that this this is done deliberately for every value here, but this need not be done. You can even put all this right from D naught through D7 right before this case, just after the begin, and put that as a single statement and dispense with the use here, and you can just stick on to whatever output that you want, only that need to be listed. I have made it deliberate because in order to drive home the point that we should not forget this. Whatever is to be forced to 0, they will have to be deliberately forced to 0, otherwise tool will not do that on its own accord. And this is a continuation of the same thing, assigning different things, and finally if you see for 1 on 1 input, you have mux 8 assigned to D7 as such, and we have one default here. There is no guarantee these inputs are exactly x, valid number here, and it may be an x, that is I do not care, or even a z, a tri-state condition, and in other cases you may not have used all these conditions. In such a case, this default is a mandatory thing, otherwise it will infer latch, and you will run into problems later on. So, and finally when there was a case, a corresponding end case must be there, and since we put a begin for the beginning of the block, there must also be end. If you forget any of this, including semicolons etc., prompt comes the error message while compiling. We have also seen full adder in our review, and this is duplicated here for ease of understanding. Say you have ABC as 3 inputs, this may be regarded as a carry in, as I mentioned here, and there will be a carry out and a sum. FA stands for the full adder, and corresponding truth table is given here. If you this is nothing but exclusive OR of 3 input exclusive OR of the inputs. If you just add up all this thing, what you get is 0 0, that is how you have got here. So, here if I add up, it will be 0 1, so and so on it goes. If you add up the last 2, it means 1 0, and if you add this one to that one, what you get is 1 1, and it is as simple as that, and hence this expression is nothing but why this bracket is put is in Verilog we can implement this using gate level primitives also. They are restricted with 2 inputs basically, and so in order to realize a 3 input exclusive OR, you will have to use 2 numbers of 2 input exclusive OR, and carry out is simply a majority logic, and you can easily infer the majority logic wherever more than two ones are there, you will see the corresponding one here, you can see here everywhere. So, there are three ways of implementation of the same full adder, and one is we have already seen right the earlier stage that we have behavioral type of level of realization. So, suppose you want if you can just put a simple arithmetic expression as such a plus b and c, and this parenthesis is only to guide the synthesis tool to make it very efficient, and if you do not put this one, it may infer as internally 2 mux and so on. Instead of that, only 1 mux will be put if you guide that synthesis tool as such. That is why this parenthesis. It is a good habit to use parenthesis freely, right. And you would notice that what we have in a single line we can realize this full adder. And another beauty of this is irrespective of the bit precision as such. Suppose you want 16-bit precision for A and B, you can still use the very same statement as such. Only thing is you will have to declare A, B to be of that precision on the top of a program that you will be covering later on as such. And another method of realizing the same thing full adder is to little two statements you will be needing. One is for majority logic realization, which you have already seen earlier. It is a ORing of A, B, B, C and C A, and then assigning it to carry out, and sum is nothing but, as I said, 2 input mux, I mean 2 input exclusive OR is being used here, and 2 times, that is the implication there. And that is called data flow realization, and this will be helpful while pipelining your design as such, and we will see more about pipelining later on. And the very same full adder depicted using gates is this, and with an end view of primitive gate implementation, it has been put in this fashion. Note that S1 is an intermediate signal which we will be using, and similarly A1 through A3 are intermediate ANDed operation here, and this you can OR these two, and once again O1 is an intermediate signal we will be using, and final result is sum and carry. And in the next slide you see the gate level implementation for same, and notice that you may have to go for say 3, 5, 7 lines here, and this is very much close, I mean akin to your standard schematic based editing as such entry, right. So here what you see is that intermediate signal what you have seen, this is to invoke primitive which is available in the libraries of Verilog. This is exclusive OR which you are already familiar, and similarly this is AND and OR, and first one stands for the output of that gate, and whereas rest will be the inputs. As I mentioned, they are all restricted to 2 inputs normally, and some offer higher inputs as well, but that is not guaranteed on all the platforms. And finally this you plow it into the next exclusive OR along with the third signal which you have not used earlier to get the final sum output here. And similarly you can AND A, B, B, C, C, A, and OR this A1 and A2 here, right, assign to an intermediate signal here, and once again you can use this and continue ORing this A3 which we have not used earlier. So thus we have got carry out as well as sum here. Before we close this session, we will see how to make a magnitude comparator as such, and let us consider these are all let us say we have two 8-bit numbers n1 and n2, and you would like to have if n1 is greater than n2, you want one output, and you can have here, and you can just label them. When we show the program as such, we will be using the very same nomenclature as such, and these are all other possibilities. Suppose you want n1 less than n2, then activate this output and so on. So, for this is for equality, this is for not equal to, this you are already familiar, exclamation mark for inverting, right, and this is symbol for less or equal to, and this is greater or equal to, and you may get confused with this symbol later on, and they are called non-blocking statement, which will be used in always block later on. We will see more details later on, and let us see how the program goes. Once again we have used an always block as such, and you have to list all the inputs either n1 or n2 here, and there will be a begin and end, and all the outputs that you have already seen are appearing here on the left hand side here, what you have seen here, and precisely the same statement which is put here as the output only need to be inserted here in this, as you have seen here. So, n1 greater than n2, and you assign it to F13, and this is the comment what you have to put. For all the other things, this is in logical equivalence, you have to put 2 equals as such, and whereas in the ordinary elsewhere other than this, you need to have only 1 equal to as such, and this is a not equal to, and less or equal to, and then greater or equal to. I think we have covered all the possibilities. Let us consider a design example using some of the methods that we have adopted earlier, and this example is a simple summation of 2 numbers, and then compare it with a preset value, and then output different results. So, for example, you have a number 1 and number 2, 2 numbers each of 8 bits, and we want to take the sum of these 2 and output here, provided enable sum is active, that is logic high as such, and further we wish to compare this sum with preset value, which is also another user input just like number 1 and number 2, and then output if the 2 matches, that is sum and preset value matches, then you say activate one match signal. Similarly, if it is sum is greater, you activate more, if it is less, activate less. It is such a simple example, and we will see how to write the code for this. We can use assign statements for this, but however always statement is a better thing, because we need to take action only when there is a change in the inputs. So, we will use the always statement as such. So, first in this always block, you say always at, this is mandatory, and list all the input variables. You should always speak in terms of signals, not variables, that is a C habit, right. So, I will just list this enabled sum and all the inputs. Then next one is number 1, and underscore 2, then there is one R missing here, then finally preset value. Now, in order to create sum, we have already seen earlier 1 bit adders as such, in fact full adder, and we have also mentioned in a behavioral statement that we can use even multi precision in that same add as such. So, we will see right now that particular thing being done here. For example, you want to have a sum output. So, what all we have to do is just write sum, then equal to, now what we have also learnt earlier how to model a mux as such. We will combine that mux in this always loop. Normally you should not use an assign for a mux inside the always block. So, that is the difference here. So, when we say, now what we want to do is we have to take enable sum into account while writing the sum. So, let us say in the mux this selector control is enabled underscore sum, and the mux is identified by this question mark symbol. And now what we want is, there are two inputs for the mux. So, the higher order input will be put here, that is what we want here, because when enable sum is 1, we want to add the two numbers. So, what we will do is, we will put that do you think this statement will work? We have not put the precision as such, it will still work, and we can also make the precision here, which is normally done by all designers, because we do not have to go to the previous wade through previous codes and find out what precision it is. So, we can write there in this statement, we can identify that by just mentioning the range as such. Say for example, 720 and so on. Will this statement still work? It won't, because we have not terminated by a semicolon here. And similarly, many people, especially novice, make the mistake of putting a logical OR as such. So, this is not a valid thing. So, what we have to do is put OR. And now similarly, we will write for the other three outputs, that is match. Here also we need to put the same signal as such. I am not writing it here. And now this time what we want to is, if it is 1, then we what we will put here is corresponding to the 1 input, and that is the sum equal to value, right. There is actually one more mistake here in this sentence. So, that is to this, what we need to put, we have forgotten another input as such for the mux. So, we will have to put a colon and then put what we want is just 0 at the output. If the enable is not valid, it is not asserted, then we need to put just 0, because we just want to make a distinction whether it has gone through the actual process or not. And similarly here we need to put 0 here. So, see this will have to put within parenthesis, and note that this is a logical statement, and for logical statement just one equal to, if you put at the compiler stage it will reject. So, what you need to put is two equal statements. For example, you want to put inversion not equal to, what all you have to do is just replace this one by an exclamation mark as such. That exclamation mark is for the logical realization, and similarly we can put less as output. And here it is, I think I have missed one thing that I can put here as well. And these are the same. Here it is less and here it is more, and precisely the same statement will appear over here. And likewise we have a 0 if the condition is not satisfied. That is to say, and as a further explanation, what we say is the sum is equal to preset value, both of which are multi-precision width as such, and what the value it returns is actually 1. Are we clear in this? Are we together in this? Okay. Then I think that is all as simple as this code. We have forgotten one more thing. Can you point out what it is? This is a multi-statement, right? So, we that is a block. So, we need to add a begin and end to that. So, we will put begin here and end here. This completes the code for this. Now, as an assignment to you, I will suggest that you add one more input here saying that sum stroke difference. This is one bit input as such. If sum is 0, what I want at this output is sum, otherwise I want difference to appear over there. So, modify this accordingly. So, in difference case, okay, let us call it by a generic name as sum d. So, the same thing will become mod of 1 then num 2. Is this clear?
Sentences we completed more 0 colon semicolon.
Yes, you are right. So, this is 0 here.
And those things are multiplication, sum is
Yes,
third statement.
this is this one.
Yeah.
No, these are all single precision. Therefore, you do not have to mention it specifically as such.
Enable sum slash difference.
Pardon?
That signal will become enable sum or difference.
No, that's okay.
Here,
That is-
no, it is a single signal as such. Right. To summarize, what we have done so far is we have used multi-precision in the place of single precision in the case of full adder as such seen earlier, and next is we have used precisely the same comparators, and that is how we have got. So, we have also combined an always block and the same thing by putting assign statements you can just make that one, but what will happen when you put assign statements it keeps on churning continuously because it is precisely the gate that is going to be mapped onto the device. So, it will be working all the time. So, if a circuit is working it consumes more power. So, the always thing is preferable because this will work only when any change is encountered there, that is all the difference. And to summarize the whole thing, we have covered simple gates and the symbol for which is ampersand and or, that is a vertical stroke, and for exclusive or cap and so on. And then we have seen how to use assign and always block in order to achieve any combination circuits. In this way you can make any complicated combination circuits as such. In the next class we will be seeing how to model sequential circuits. Thank you.